Wow. Okay, so welcome to the first edition of Papers We Love, or it might be Papers We Hate, but the general idea is that we will go with the interesting, intriguing, controversial articles, white papers, or whatever we feel that it's interesting. And today we will start with the white paper, pretty old white papers from 1987, and this will be the white paper with the title Sagas, and it's the initial white paper that introduces saga concept, and it was written on Princeton by Hector Garcia-Molina and Kenneth Salem. So we will go through the whole document. I'm not sure how long will it take us. We'll see. But I will be adding my commentary as we go. And also don't be shy to interrupt me or write on the chat window if you have any questions, because then it will be even more interactive. And I can say that I read this paper, but some time ago, so I don't remember the details. And I will do a bit of try because I would like to start with why I believe that this concept is interesting and important, and how am I describing sagas in my typical workshops, and then we'll see how far I am from the original white paper and the original idea. So I hope that I'm not far from that. Does it sound okay to you, or do you have any questions? Hey, Frank, nice to see you. Okay, so I will start, and feel free to interrupt me or ask question via voice or via chat. So in general, when we started our industry, I'm almost 30, but I'm not old enough to make such a bold statement, but still most of the systems were running on the single computer. And on the single computer, and that I'm old enough to remember that, we had everything. So we had our database, we have our services, etc. And typically for those scenarios, saving and storing is not that extremely complicated. So if we have database and we have application, then if we are trying to make more than one operation, then we can close all of those database operations within a single transaction. And thanks to that, we can get all those guarantees that we expect from the database, like atomicity, isolation, etc. So I'm sure that you know.
No.
So I'm sure that you all know that already, but just to be sure that we are on the same page. So this is how the classical transaction processing looks like for the single coordinator and the single database. So at first we are sending the prepare statement, and we are saying this is what we aim to be storing. And then database is returning as information that that's fine. I can proceed with that. And then we are saying then, okay, then commit it. And if everything is still okay, then database will commit transaction, make all the necessary changes, and call it a day. So simple as that. But of course, in the meantime, between one transaction and the other, depending on our isolation level, it might happen that someone in the meantime was faster and was able to commit their own transaction faster. So then we might need to say, okay, then if I cannot do that, then roll back those changes, and database will make sure that we don't have any leftovers. And situation is getting much more complicated if we are trying to perform multiple changes to multiple databases, so to multiple nodes. And at first we need, so it might be that we want to store all those information in all those databases, the same information, the same set of changes. Or we might, for example, have distribution that one database is storing data for one module, the other for the other, and so on and so forth. Or for example, one database is storing information for one customer, the other for the other. It doesn't matter how we partition or shard, the problem remains the same. So at first we are saying to each of the databases, to each of nodes, that this is the set of changes that we would like to be do and to update. Then databases, if everything works well, then all of those databases at some point, one by one or in parallel, will send us information that, yeah, we are good to go. So then we are saying, okay, then if you're good to go, then commit that. And if everything went smoothly, then we have all of the changes stored in the database, and cool, sounds fine. However, if one of those databases would say that, nah, you cannot do it, then we need to roll back all the changes to other databases that already said that, yeah, I'm snapshotting the state, I'm making the changes, just tell me when the transaction has finished. And unfortunately here, we need to do the rollback. So it's enough to have a single node or single database that is failing here. And then we need to roll back everything. And it doesn't have to be, doesn't have to mean that we have just failed on some constraint, so we didn't run our business logic correctly. It might just mean that we had some transient connectivity issue, etc. And I tried once to configure in my project distributed transaction. It was working for some time, and from time to time on the staging environment, I even managed to get it to pre-prod, but then I said that, no, just don't do it. And I was really happy afterwards, after that decision, because as you see, maintaining that and making that work is extremely sophisticated, and it's really fragile construction because we need to have a high availability on each of those nodes that are involved in the transaction. And this process in general is called two-phase commit, because at first we are saying what we want to do, then we are getting from all the participants, the coordinator is getting information that, yeah, that's fine, let's proceed. And then we need to do the final commit once the changes were made, or rollback if something failed. So this is extremely fragile. So I'm curious if any of you also tried to configure distributed transaction like MSDTC. That's what I tried. So Microsoft distributed transaction. So yeah, if just a single node failed, then in general, everything fails. So this is not a pleasant experience. And of course, we might say that, why am I talking about that? Luckily, I'm not using distributed transaction, but actually we do, because if we are doing communication between our services, and even if we have multiple databases, so best practices of managing our cases, then actually we are doing distributed transactions, because it's enough that if our process requires to make changes to multiple services, then if we don't have some better mechanism and we are doing everything sequentially, then if one of those services are failing, is not available, then our whole process will fail. So we are replacing the technology like I mentioned, Microsoft distributed transactions, with our half-baked and homemade coordination. And whether this is fragile or not, then obviously it is. So we are just replacing the distributed transaction with the implicit distributed transactions. So let's have a look on what Hector Garcia-Molina and Kenneth Salem wrote and what was their goal and what were they aiming to. So do you have any questions or comment at that time? Okay, then I will be reading the article, and feel free to interrupt me or ask questions. I will also try to make commentary. See, 1987. I was 2 years old at that time. Cool. So let's start with the summary. Long-lived transaction, so LLTs, hold on to database resources for relatively long periods of time, significantly delaying the termination of the shorter and more common transaction. To alleviate these problems, we propose the notion of a saga. A LLT, so long-lived transaction, is a saga if it can be written as a sequence of transactions that can be interleaved with other transactions. Okay, sounds like we would like to have some breakdown into smaller pieces and better isolation. So the database management system guarantees that either all the transactions in Saga are successfully completed or compensating transactions are run to amend a partial execution. So sounds like they would like to replace the rollback with something else. We'll see. Both the concept of Saga and its implementation are relatively simple. And simple is a really dangerous word, but let's go. But they have the potential to improve performance significantly. Cool. We analyzed the various implementation issues related to Sagas, including how they can be run on an existing system that does not directly support them. We also discussed techniques for databases and LLT design that make it feasible to break up into Sagas. So it's clearly visible even at that point that there is no notion of managing business processes here. It's clearly said that we would like to achieve something that will help us to better roll back the changes, get the better isolation, and don't have the lowest common denominator. So having one long-lived transaction that is impacting the regular processing and have the better resiliency. So let's go with the introduction. As its name indicates, a long-lived transaction is a transaction whose execution, even without interference from other transactions, takes a substantial amount of time, possibly on the order of hours or days. Whoa. Luckily, the meaning of the long-lived transaction changed in those almost 40 years. So 35 years ago, long-lived transaction could span hours or days. I mean, technically you can still have it, but I think that right now long-lived transaction would be a minutes or hour. That's extremely long. But side note. A long-lived transaction, or LLT, has a long duration compared to the majority of other transactions, either because it accesses many database objects, it has lengthy computations, it pauses for inputs from the users, or a combination of those factors. And I think that's quite important here, because typically nowadays, if we are looking from the database perspective, then those database transactions, at least in the majority of the modern services, we are not opening transaction and doing like a pessimistic logging that, for example, someone opens some web form, then we are starting transaction, and then user is performing some operation for days or hours, and then we are shutting down the transaction. So that's something that I hope that we are not doing anymore too often. I saw that in past, but luckily not so much. However, that doesn't mean that this statement is outdated, because remember, this is precisely also the distributed transaction and long-lived transaction, because during this process, we might have some, like we can store some partial result, and then we can have an implicit long-lived transaction. So we might be waiting until someone um, uh, approves some part of the process. So user interaction is still possible, however, not from the technical concept, but more logical. I hope that you agree. Examples of LLTs are transaction to produce monthly account statement as at a bank, transaction to process claims at an insurance company, and transaction to collect statistics over an entire database. So here we are getting into some areas that that are touching the business processes, because I remember even a years ago, like there was a big movement. Like previously, we had most of our business logic stored in database, in stored procedures. So all of the things that were described here. And right now, I think that only like a business intelligence and business analytics are still happening so much in database. And that's fine, actually. In most cases, LLTs present serious performance problems. Yes, that's correct. If they are running for days, obviously. Since they are transactions, the system must execute them as atomic actions, thus preserving the consistency of the database. So, as I mentioned, all those atomicity, isolation guarantees, etc. So if those transactions were running for days, then yeah, the database need to take huge amount of things into an account while performing operation. To make a transaction atomic, the system usually locks the object accessed by the transaction until it commits. And this typically occurs at the end of the transaction. So yeah, it's like a pessimistic locking, because then we are saying that we already know that no one else should be changing this specific object. And if that's touching a single row, that's not a big deal. But if we are doing the account statements or some insurance reports, then definitely they are touching more than one, and that's an issue. As a consequence, other transactions wishing to access the long-lived transactions objects suffers a long locking delay. Yeah, so we are getting the ripple effect, so cascading failure if the initial long-lived transaction is failing. So if LLTs are long because they access many database objects, then other transactions are likely to suffer from an increased blocking rate as well. They are more likely to conflict with an LLT than with a shorter transaction. Yeah, okay. Because then we might be, the risk of clashing is increasing, because we have usually a huge queue of to be committed transactions. Furthermore, the transaction abort rate can also be increased by LLTs. As discussed, in the frequency of deadlock is very sensitive to the size of transactions. That is, to how many object transaction access. So yeah, that's what I mentioned. If it's a single row, that's not a big deal. If more than one, that's getting worse. In analysis of Gray, the deadlock frequency grows with the fourth power of the transaction size. Oh, that's interesting. I didn't know that. Hence, since LLTs access many objects, they may cause many deadlocks and correspondingly many abortions. From the point of view of system crashes, LLTs have a higher probability of encountering failure because of their duration, and are thus more likely to encounter yet more delays and more likely to be aborted themselves. So just to visualize that. Okay, where is my Miro board? Okay, so this is our webinar about distributed transactions. So if we have a long living transaction, so this is a long living transaction, and a set even corresponding shorter transactions, and they all need to update the same set of resources, then all of those smaller transactions, if this one is started, then they cannot be completed. We need to move them in our timeline further on. And so if this long-lived transaction is kept along, then all of them need to wait. And if this transaction will fail, then all of those smaller transactions will need to be also aborted. And also it works the other way around. So it's enough that only this small transaction will fail, then also this, if it's the first one or like in the middle, and all the others will also need to be cancelled. So not perfect. In general, there is no solution that eliminates the problem of long-lived transactions. Even if we use mechanism different from locking to ensure atomicity of the LLTs, the long delays and or the high abort rate will remain. No matter how the mechanism operates, a transaction that needs to access the objects that were accessed by long-lived transaction cannot commit until LLT commits. So yeah, so we can do some fancy stuff, even AI analysis, but eventually we might be just making this issue smaller, but it will still remains. That's fair. However, for specific applications, it might be possible to alleviate the problems by relaxing the requirement that an LLT be executed as an atomic action. In other words, without sacrificing the consistency of the database, it might be possible for certain long-lived transactions to release their resources before they complete, thus permitting other waiting transactions to proceed. To illustrate this idea, consider an airline reservation application. The database, or actually a collection of databases from different airlines, contain reservation for flights, and a transactions T wishes to make a number of reservations. For this discussion, let us assume that T is a long-lived transaction. Say it pauses for customer input after each reservation. In this application, it might not be necessary for T to hold on to all of its resources until it completes. For instance, after T reserves a seat on flight F1, it could immediately allow other transactions to reserve seats on the same flight. In other words, we can view T as the collection of sub-transactions T1, T2, Tn that reserves the individual seats. So if we use something like that, then instead of keeping a big long-lived transaction, then we are breaking it down into a smaller ones. So and if we know that this is touching F1, so flight 1, F4, then as soon as we proceed and manage to complete those 3 updates, then we immediately can commit and free F flight 1 resource for the other transactions, because we know that there is no other touching F1 and actually also F2 here. So we could make this process like that. So at this point, we can commit F1, at this one F2, and free up the resources for others. And each of this will be like a T1. This will be a T1. This will be T2. And so on and so forth. I hope that you agree with me. If not, then feel free to comment if that makes sense. If I'm also going too slow or too fast, feel free to tell me that I should stop those side notes. So again, in other words, we can view T, so the transaction, as a collection of transactions T1, T2, Tn that reserve an individual seats. Okay, so my is not correct. In our case, the shared resource is not flight by seat. So we would have something like that. But yeah. However, we do not wish to submit T to the database systems, DBMS, simply as a collection of independent transactions, because we still want T to be a unit that is either successfully completed or not done at all. We would not be satisfied with a DBMS that would allow T to reserve 3 out of 5 seats and then, due to a crash, do nothing more. On the other hand, we would be satisfied with a DBMS that guaranteed that T would make all of its reservation or would cancel any reservation made if T had to be suspended. So if this one would fail, so if the seat number 4 is reserved, then we should also cancel all those previous reservations or operations. Okay, this example shows that a control mechanism is that is less rigid than the conventional atomic transaction ones, but still offers some guarantees regarding the execution of the components of a long-lived transaction would be useful. In this paper, we will present such a mechanism. Let us use the term saga to refer to a LLT, so long-lived transaction, that can be broken up into a collection of sub-transactions that can be interleaved in any way with other transactions. Each sub-transaction, in this case, is a real transaction in the sense that it preserves database consistency. However, unlike other transactions, the transactions in a saga are related to each other and should be executed as a non-atomic, unit, any partial executions of the saga are undesirable, and if they occur, must be compensated for. So in other words, we are trying to break this transaction and all of those operations that we want to be doing to some specific objects. And each of this atomic update is like a small transaction. So it stores partially the information and commits that. So it's like a single small piece of a change, but logically it's also grouped into a saga, which is like a transaction of small transactions. So like a group or actually a sequence of transactions, small transactions. To amend partial executions, each saga transaction T should be provided with a compensating transaction C1. The compensating transaction undoes, from a semantic point of view, any of the actions performed by T number, but does not necessarily return the database to the state that existed when the execution of TI began. In our airline example, if TI reserves a seat on a flight, then CI can cancel the reservation, say by subtracting any from the number of reservations and performing some other checks. So again, this is really interesting how our industry changed in the recent years. So typically advice of running such transactions on database would be the ill advice. However, remember, we are right now in 1987. And we are also looking on that not only from the technical standpoint, but because right now, nowadays, Saga is more connected to the business processes. So in that sense, that's kind of matching. So again, in our airline example, if TI reserves a seat on a flight, then CI can cancel the reservation. But CI cannot simply store in the database the number of seats that existed when TI ran, because other transactions could have run between TI reserved the seat and CI canceled the reservation and could have changed the number of reservation for the flight. So I would give the other example. So for example, if we are making a payment and we paid, for example, for some gift for a Christmas at our favorite online shop. And let's say that we would like to cancel this payment, but it might appear that this shop doesn't have any money because they already used that, so they cannot compensate it. Or in this example, it might mean that as we reserved the seat, then someone else made also the reservation. If we can have more than one, then just simply canceling, we would need to take a lot of things into an account. We might not be even able to compensate that. So I think that this part, if I understood it well, highlights also that we are not always able to get to the initial state before we perform a certain operation. Okay, let's move on. Once compensating transactions C1, C2, Cn, yada yada, are defined for Saga T1, T2, Tn, then the system can make the following guarantee: either the sequence of transactions, which is the preferable one, or the sequence T1, T2, T something compensation for T2 and T1. So this is the case where, for example, fifth sub-transaction failed or fifth step failed, and we need to compensate all the previous one. Note that other transaction might see the effects of a partial Saga execution. When a compensating transaction C1 is run, no effort is made to notify or abort transactions that might have seen the results of TI before they were compensated for CI. So nowadays, some databases, like I believe SQL Server, allows to have read uncommitted. Not all databases allow that. For example, Postgres only allow to have read committed, which still allows to see some partial results. But depending on the isolation level, we might have that option already baked in our databases. I'm not sure if that was possible also in 1987. That's curious things. Sagas appear to be a relatively common type of long-lived transactions. They occur when long-lived transactions consist of a sequence of relatively independent steps, where each step does not have to observe the same consistent database state. For instance, in a bank, it is common to perform a fixed operation, for example, compute interest on all accounts, and there is very subtle interaction between the computations for one account and the next. In an office information system, it is also common to have long-lived transactions with independent steps that can be interleaved with those of other transactions. For example, receiving a purchase order involves entering the information into database, updating the inventory, notifying accounting, printing a shipping order, and so on. Printing part of database transaction. Interesting. Such office long-lived transaction mimic real procedures and hence can cope with interleaved transactions. In reality, one does not physically lock the warehouse until a purchase order is fully processed. Thus, there is no need for the computerized procedures to lock out the inventory database until they complete. An inventory is a good example because inventory is usually showed like the most common cradish approach where you can predict everything and just update the state. While in inventory or in warehouse, it might be that our system tells that we have a few items still in a warehouse, but it might appear that someone stole it, that we have a leaking roof that destroyed, like flooded this set of equipment, and so on and so forth. So yeah, that's a good point, that we should embrace that our systems might not be perfect and that we cannot have all the data there because the physical world is much more fuzzy. Once again, the bank and the office LLTs we have presented are not just collection of normal transactions, they are sagas. There is an application constraint, not representable by the database consistency constraints, that the steps of these activities should not be left unfinished. The applications demand that all accounts be processed or that the purchase order is fully processed. If the purchase order is not successfully completed, then the records must be straightened. For instance, inventory should not reflect the departure of the item. In the bank example, it may always be possible to move forward and finish the LLT. In this case, it might not be necessary to ever compensate for an unfinished long-lived transaction. So I believe that's also an important line. So the application demand. So here we are getting introduced that what we have in our state and the consistency, like a physical consistency of our database and our data model, might not be the same as our application requirements. So that's an important split. So the physical storage model and the applications that are more related to how we are running the business instead of how we are technically solving that. The notion of saga is related to several existing concepts. For example, a saga is like a nested transaction, except that a saga only permits two levels of nesting. The top level saga can end simple transaction, and at the outer level, full atomicity is not provided. That is, saga may view the partial results of other sagas. So it's close to like a return committed from the physical database perspective, or read committed more likely, but not like a serializable. So we don't need to put all transaction in a sequential order, but we might interleave what we already committed. Sagas can be also viewed as a special type of transactions running under the mechanism described in some other paper. The restrictions we have placed on the more general mechanism make it much more simpler to implement. Again, I would be careful with that. And understand sagas. In consequence, making it more likely that they be used in practice. And keeping in mind how how much discussion I had in past, and I will definitely had about sagas, I wouldn't say that they are super easy to understand. Although I would say it's a simple, but simple is not always easy. So yeah, side note. Other related ideas include which describes independent atomic actions similar to sagas, and which considers long-lived transaction as consistency, atomic, durable, environment, impact. I'm not sure what's impact. Curious if any of you knows that acronym. A distributed database application described uses suspense files containing update transactions to be run at remote systems to implement updates of replicated distributed data. Okay, doesn't sound compelling. Two ingredients are necessary to make Sagas feasible: DBMS that supports Sagas and LLTs that are broken into sequences of transactions. In these papers, we focus on how to obtain these ingredients in a centralized database system. Note that since the concept of Saga is quite simple, one does not require complex or novel implementation mechanism. As a matter of fact, as discussed in section 7, Sagas can be fully implemented on top of existing DBMS. Thus, the emphasis in this paper is not on presenting the novel implementation techniques, but on suggesting appropriate ones for a simple, clean, and efficient implementation of Sagas. Okay. In section 2 through 7, we studied the implementation of Saga processing mechanism. We start by discussing how an application programmer can define Sagas and then how the system can support them. We initially assumed that compensating transactions can only encounter system failures. Later on section 6, we studied the effects of other failures in compensating transactions. Due to space limitations, we only discussed Sagas in a centralized system, although clearly they can be implemented in a distributed database system. So see, we already had distributed systems in 1987. Not surprised, but yeah, joke. In section 8 and 9, we address the design LLTs. We first show that our model of sequential transaction execution for a Saga can be generalized to include parallel transaction execution and hence a wider range of LLTs. Then we discuss strategies that an application programmer may follow in order to write LLTs that are indeed Sagas and can have advantage of our proposed mechanism. Okay. So sounds like I better move a bit faster because we are at point 2. But I think that it's worth understanding the issue that we are trying to solve. So user facilities. From the point of view of an application programmer like me, A mechanism is required for informing the system of the beginning and end of a saga, the beginning and end of each transaction, and the compensating transaction. This mechanism could be similar to the one used in conventional systems to manage transactions. I mean, yeah, of course. It's good to know whether we succeeded or we had some partial issues and it was compensated. In particular, when an application program wishes to initiate Saga, it issues a begin Saga command to the system. This is followed by a series of begin transaction and transaction commands that indicates the boundaries of each transaction. Between transaction, the application can perform operations that do not involve access to database, such as manipulation of local variables. Okay. Within a transaction, the application can issue conventional database access commands. In addition, it can optionally start a user-initiated abort by issuing an abort transaction command. This terminates the current transaction, but not the saga. Similarly, there is an abort saga command to abort first the currently executing transaction and second the entire saga by running compensating transactions. Finally, there is an end saga command to commit the currently executing transaction, if any, to complete the saga. So if we get back here, then each of these sub transactions or transactions actually, each of them will have a command. So at first we will have, maybe let's do it like that. So start saga, and then we will have begin and end transaction. And we will have that for each of those subsequent transactions. And in the end, we will have end saga. So, and actually this will be run like that. So in the sequential order. And each of that can be triggered by some application. So actually from the user or from the computer. So our service, so our application layer. Each our business logic can decide that we would like to end transaction and or perform any other operation. So like abort saga, abort transaction. So we are moving the coordination from the database to application layer, which is kind of interesting because then we are saying that we are embracing that our business logic might know better whether we should compensate or not, or fail or not, which is not always the case, but introducing this concept and this notion of the business information, I think that's really important. Most of the commands will include various parameters. The begin saga command can return a saga identifier to the program. This identifier can be passed to the system on subsequent calls made by the saga. An abort transaction command will include as a parameter the addresses where saga execution is to continue after the abortion. Each end transaction call includes the identification of the compensating transaction that must be executed in case the currently ending transaction must be rolled back. The identification includes the name and entry point of the compensating program, plus any parameters that the compensating transaction may need. We assume that each compensating program includes its own begin transaction and end transaction calls. Abort transaction and abort Saga commands are not allowed within a compensating transactions. So if we are already compensating, then we cannot interfere with that. We need to proceed. Finally, the abort Saga command may include as a parameter a save point identifier that as described below. So I think that this part is really important, because based on that one, an abort transaction command will include as a parameter the address where Saga execution is to continue after abortion. Then that means that, at least in my interpretation, I'm curious about yours, that really the application layer is a decision maker, and Saga doesn't need to know and doesn't need to maintain any other indication than what's the current step. And because by that you can only say whether you can end transaction, abort or not. So it only contains identifier, so we need to store it somehow, and the current step we are in. But the rest of the decision making and actually the states should be stored somewhere else. Or decision making is not in the database, but in the application layer. Note that this is possible to have each transaction stored in the database the parameters that its compensating transaction may need in the future. In this case, the parameters do not have to be passed by the system. They can be read by the compensating transaction when it starts. Also, note that if an end Saga command ends both the last transaction and the Saga, there is no need to have a compensating transaction for the last transaction. If instead a separate end transaction is used, then it will have to include the identification of a compensating transaction. So it means that if we are finishing a specific step, then we need to tell what's next, because database won't know. We just need to tell that, hey man, if this failed, then you need to compensate it like that, and this is what's next. In some cases, it might be desirable to let the application programmer indicate through the save point command where Saga checkpoints should be taken. This command can be issued between transactions. It forces the system to save the state of the running application program and returns a save point identifier for future reference. The save points could then be useful in reducing the amount of work after a Saga failure or a system crash instead of compensating for all the outstanding transactions. The system could compensate for transaction executed since the last set save point and then restart the Saga. Okay, so we might be having some snapshot. And that's also something that we can do in databases like in Postgres. You can have a snapshot for a specific transaction. So snapshot at which was your database. But this is an optional thing. Of course, this means that we can now have execution of type 1, 2, compensating 2, T3, T4, T5, compensating T5, T4, T5, T6. So it means after successfully executing step 2 the first time, the system crashed. A save point had been taken after first step, But to restart here, the system fares and does T2 by running compensating operation 2. Then the Saga can be restarted and T2 re-executed. A second failure occurred after the compensation of T5. This means that our definition of valid execution sequences given above must be modified to include such sequences. If these partial recovery sequences are not valid, then the system should either not take save points or it should take them automatically at the beginning or end of every transaction. So like a snapshot. But this is interesting that it doesn't mean that the whole Saga will fail if you start some compensating operation. So you can have like a partial failure, then recover and proceed. I mean, in the reality, that's also possible. Like, for example, if you try to pay it with PayPal and you didn't have money, and then you put some money quickly into an account, then you can retry and proceed. Or if you are using some Stripe, then you might choose different ways how to pay for that. So you might use just different payment provider. So that's also valid from the business standpoint, but I didn't know that. The model we have described up to now is the quite general, but in some cases it might be easier to have more restrictive one. We will discuss such restrictive model later on section 5. Saving code reliably. In a conventional transaction processing system, application code is not needed to restore the database for a consistent state after a crash. If a failure destroys the code of a running transaction, the system logs contains enough information to undo the effects of the transaction. In a Saga processing system, the situation is different. To complete a running Saga after a crash, it is necessary to either complete the missing transactions or to run compensating transaction to abort the Saga. In either case, it is essential to have the required application code. Yeah, because application code is telling how you compensate and what are the next steps. Transaction systems that use abstract data types face a similar problem. Recovering an abstract data object can involve logging operations, an inverse operation. I'm not sure what he means by that. On that type, rather than old and new values. Thus, code to implement this operation must survive if the database is to be restored to a consistent state after a crash. So that also relates to our microservice thing. If the microservice doesn't wake up, then our retry policy won't help and we won't be able to proceed. So yeah, as a general rule, that sounds good. There are various possible solutions to this problem. One is to handle application code as system code is handled in conventional systems. Note that even though a conventional DBMS needs to save application code reliably, it must save system code. That is, a conventional DBMS cannot restart a failure if a failure destroyed the code requires to run system. Thus, conventional systems have manual or automatic procedures outside of DBMS itself for updating and storing backup copies of the system. So it sounds like some blockchain people read this article because those smart contracts have both data and the code is frozen to be able to be predictable and do the same stuff. And the other thing is nowadays we have in databases those shutting the completing transactions after the database was restored. So once I thought that it's not the case. And I had a really long-lived migration, and I thought that if I just kill the database and restart it, then it will stop processing this transaction and immediately abort it. But not that. I learned hard years ago that it's not the case. So if you have the transaction, then nowadays databases are smart enough to continue them after rollback. So at least we have that already baked in. In a Saga processing system, we could then require that application code for Sagas be defined and updated in the same fashion. Each new version of a program created would be stored in the current system area. Current system area sounds smart. As well as in one or more backup areas. Since the updates would not be under the control of DBMS, they would not be atomic operations and would probably require manual intervention. In case a crash occurs during the update, when a Saga starts running, it would assume that all transactions and compensating transactions have been predefined, and it would simply make the appropriate calls. Such an approach may be acceptable if Sagas are written by trusted application programmers and not updated frequently. Not updated frequently. Famous last words. Okay. If this is not the case, it might be best to handle Saga code as part of the database. If Saga code is simply stored as one of or more database objects, then its recovery would be automatic. The only drawback is that the DBMS might be able to handle large objects, in example, the code. Some systems would not be able to do this because their data model does not permit large unstructured objects. The buffer manager cannot manage objects that span more than one buffer or some other reason. Yeah, luckily we nowadays don't have so much limitations, and we can also include our stored procedures as part of the recovery. And from the technical standpoint, so purely technical understanding of the Saga, each statement in stored procedure is like in some databases like Postgres can be treated as a separate statement that might be immediately committed. So in that sense, it's like semi-automated Saga processing baked in, at least per my understanding. If the DBMS can manage code, then reliable code storage for Sagas becomes quite simple. The first transaction of the Saga T1 enters into the database all further transactions, compensating or not. That may be needed in the future. When T1 commits, the rest of the Saga is ready to start. The compensating transaction for T1, C1, would simply remove these objects from the database. It is also possible to define transactions incrementally. For example, if a compensating transaction C1 needs to be entered into the database until its corresponding transaction T1 is ready to commit. This approach is slightly more complicated but saves unnecessary database operation. So it means that we would have some sort of stack where we would put one by one or possible like an algorithm, like so we would store all of our commands that might be, and we will be just moving through this. It's like, maybe let's do it like that. So we would say that if we are here, then maybe let's make it a bit bolder. Yeah, so if we are here, then we are committing this transaction. If all went smoothly, then we are going to T1, and those two are not needed anymore. And if we compensate, then we are here, and we can either retry and from compensating Just abort transaction or go to the next step if it's just some recoverable partial failure. But still we are just storing some script or set of instructions, but not the application logic, which the application logic should be still in the some sort of application, whatever it is. Backward recovery. When a failure interrupts Saga, there are two choices: compensate for the executed transactions, backward recovery, or execute the missing transactions, forward recovery. Of course, forward recovery may not be an option in all situations. For backward recovery, the system needs compensating transactions. For forward recovery, it needs save points. So let's say that we have T3. So backward recovery means that we are here. All those three, all T1 and T2 succeeded, but T3 failed. So we are not even committing it. Then we are moving backwards. So we are going here, and so we are compensating transaction 2, and we are compensating transaction 1. And this is the backward recovery in my understanding. And forward recovery means that if this is our, if we committed those two transactions and we have, not this one, and we shut down our state at this point. So this is our save point, and this transaction is failing, then we know that those two were already saved, and instead of it, then we can, so that it will go this way. So we are compensating transaction 3 and then going to save point, and we can forward. At least that's my current understanding. So we might retry that from the save point, because we know that this is already saved and we can continue and move forward. We'll see. In this section, we will describe how pure backward recovery can be implemented. The next, we'll discuss mixed backward, forward, and pure forward recovery. Within the DBMS, a Saga execution component, SEC, manages Sagas. Saga execution component sounds posh. This component calls the conventional transaction execution component, TEC, which manages the execution of the individual transactions. So my understanding is that TEC is our controller that runs a single transaction and ensures that it's atomic, isolated, durable, yada yada. The operation of the SEC, so Saga execution component, is similar to that of the TEC. The SEC executes a series of transactions as a unit, while the TEC executes a series of actions as an atomic unit. Both components require a log to record the activities of Sagas and transactions. So we could wrap it, this one, and this is what we have as our write ahead log or transaction log. So set of instructions that we need to perform to have the whole transaction shut down. So write ahead log or transaction log, depending on the database. All the databases works like that, or most of them. So log, not like a logging from an application standpoint, but the data structure that keeps information about what's happening and what's actually happened and what we need to shut together. As a matter of fact, it is convenient to merge both logs into a single one, and we will assume that this is the case here. Interesting. So it would look like that. So this is the main one. Let's do it here. Okay, this is our main one. And here we are getting those. This is our sec, and this is our transactions execution control. So merged together, which makes sense because if we need to proceed all of those smaller transactions sequentially, then it's fine to merge all of that into a bigger sequence. So this will be our sec, and this will be our tech. Thanks, Martin. Glad that those visualizations are helpful. I was wondering whether this is helping or more making more blurring the whole picture. So yeah, I mean, it kind of makes sense because if it's said that our saga needs to be processed in a specific sequence of operation, then why not? And all of that in the end has to be either completed or not, to some understanding of completeness. Note that the sec needs no concurrency control because the transaction it controls can be interleaved with other transactions. So that means that if we had other saga, then once we shut down the specific transaction, then other saga can interact with it. It's not like within a single saga. All saga commands and database actions are channeled through the sec. Each saga command, for instance, begin saga, is recorded in the log before any action is taken. Any parameters contained in the commands, for instance, the compensating transaction identification in an end transaction command, are also recorded in the log. The begin transaction and end transaction commands, as well as all database actions, are forwarded to the tag, which handles them in a conventional way. So again, this is like our classical store transaction, and this is like the main one. And it's important to say, let me try to move it, that and highlight again that if we are ending transaction, then we need to provide a next step. So this is really important. It's not like it will happen automatically. We need to tell what's next. So provide all the information necessary while completing the specific transaction to make the routing to the next transaction. At least that's my understanding. Okay. When the sec receives an abort saga command, it initiates backward recovery. To illustrate, let us consider a saga that has executed transaction T1, T2, and that halfway through the execution of T3 issues an abort saga command to the sec. The sec records the command in the log to protect against a crash during rollback, and then instructs tech to abort transaction T3. This transaction is rolled back using conventional techniques by storing the before values found in the log back into the database. Next to the sec consults the log and orders the execution of compensating transaction C2 and C1 if the parameters for these transactions are in the log. They are extracted and passed in the call. The two transactions are executed just like other transaction. And of course, the information as to when they begin and commit is recorded in the log by tech. If there is a crash during this time, the system will then be able to know what work remains to be done. When C1 commits, when compensating one commits, the saga terminates. An entry is made in the log, similar to the one created by the end saga command. So we would have like a begin transaction T1. Then we would have end T1. We would have the same for T2. And then we would have the T3 begin transaction, sorry. And we would have abort, was it abort saga or abort saga? Okay. Let's say S1. So then we know that if we started to begin this transaction, then we can take the data from here, because in begin transaction, we should tell what is the step, like compensating step, as at least per my understanding. We take the data from that, and then we are running the compensation of the C3. Then once we compensated that, then we are moving here, here to the T2, and this block, I'm not sure why is it not working. Yeah, so again, we are moving here to T2, and in this command, we should be having information about the compensation. Then we are running C2 if it succeeded. And then if not, then we are, and in the end, we are running C1. And after C1, we have the transaction, the saga completed. The saga terminates. So it should probably have some terminate saga stored somewhere, because if we don't store this information in the log, then it will probably try to again run this until this is visible. So by maintaining such a simple saga log, like a sequence of comments, we know precisely what has happened and what we need to do, at least from the sequence standpoint, because of course we need to keep all the information in the log to be able to recover. So the log is also used to recover from crashes. After a crashes, the tech is first invoked to clean up pending transaction Once all transactions are either aborted or committed, the SEC evaluates the status of each saga. If a saga has corresponding begin saga and end saga entries in the log, then the saga completed and no further action is necessary. If there is a missing end saga entry, then the saga is aborted. By scanning the log, SEC discovers that the identity of the last successful executed and uncompensated transaction. Compensating transactions are run for this transaction and all preceding ones. Forward recovery. So I think that, okay, we have a question. What happens if a compensating transaction failed, like T2 in Miro? Let's say you retry it and it fails again. When do you do with the saga if a C2 CN fails and it cannot proceed? So the transaction execution component ensures that if the transaction has started, then it needs to be then it will be restarted after the database server failure. So if it fails, then and restarts, then the transaction will be continued, and either it failed or succeed. So that's the theory. Of course, we might have like our disk were totally destroyed, etc. So we might have some unrecoverable failure, but that's another story. But the first thing, and it's written here, that after a crash, the transaction execution component is first invoked to clean up pending transaction. So it looks on top of the each log. So like here, we see that we have begin transaction and it didn't, or we had some end transaction and that wasn't completed. It tries to complete. And then based on this decision and the data it has, so it's important that in end transaction, we keep what is the compensating operation if we need to do backward recovery, or so we are just, if something failed, then we are trying to move backward. And if compensating fails, then in my opinion, the compensating operation should also have information, because technically compensating operation, it was earlier written that it also might not succeed. So I would treat compensating operation as just another step that actually just tries to compensate. Like it's just marked as the compensating steps, but the compensating step might also have some other potential compensation. Or so in the worst case, if the compensating for T2 fails, then it can either go further to C1 and ignore that this has happened, or maybe just tries to abort the transaction completely. But we need to distinguish two types of failure. One is the failure that database crashed and it needs to be restarted, and that should be handled by database, by the transaction execution component. But if it fails for some other reason, like the constraint, then we should technically keep that information inside what to do, and application should decide whether we should compensate or not, because that's out of the scope of the database, at least per my understanding of this, what is written in this document. I'm not sure, Martin, if you agree or if that's that sounds okay to you also. Yeah, sounds fair. Okay, thank you. I mean, I'm reading that for the first time for a long time, so this is my interpretation. I might be wrong, of course. So let's move to forward recovery. For forward recovery, the Saga execution component, cheers. The Saga execution component requires a reliable copy of the code for all missing transactions plus a save point. So by code, it means that the procedure, what to do next. So application layer potentially. So again, smart contracts, hello, blockchain. Yeah, never mind. The save point to be used may be specified by the application or by the system depending on which aborted the Saga. Recall that a save point identifier can be included as a parameter to the abort Saga command. In the case of a system crash, the recovery component can specify the most recent save point for each active Saga. To illustrate the operation of the SEC in this case, consider a Saga that executes transactions T1, T2, a save point command, and transaction T3. When during the execution of transaction T4, the system crashes, upon recovery, the system must first perform a backward recovery to the save point, aborting T4 and compensating T3, after ensuring that the code for the running T3 and T4 is available. The SEC records in the log its decision to restart and restarts the Saga. We called it this backward forward recovery. So I think that it's quite aligned to what we discussed before. So at first we tried to compensate what failed, and then we are reaching the save point and again make decision what we should do next. So we did a backward recovery just to try to again to move forward. So at least, I mean, it might be just my confirmation bias that I would like to confirm what I interpreted before, but sounds fair to me. As mentioned in the section 2, if save points are automatically taken at the beginning of every transaction, the pure forward recovery is feasible. If we in addition prohibit the use of abort Saga commands, then it becomes unnecessary to ever perform backward recovery. Abort transaction commands would be still acceptable. This has the advantage of eliminating the need for compensating transactions, which might be difficult to write in some application. In this case, the SEC becomes a simply persistent transaction executor, similar to persistent message transmission mechanism. After every crash, for every active Saga, the SEC instructs the transaction execution component to abort the last executing transaction, and then restarts the Saga at the point where the transaction has started. So I interpret that in the sense that the initial and the backward recovery means that we are just storing what's the current, like we are just shutting the current state. So we have the Saga ID and what's the current step, and potentially information about what should be compensated. So in that sense, Saga cannot be run automatically without the application code. But if we keep both application code and not allow to abort the whole transaction, then we can have some sort of automated state machine. But that requires to keep the both code aligned and frozen to some degree, so or at least versioned or backward compatible, depending on our strategy, and also the state. So then if we keep all the information in the log, so in those commands as we discussed, so we are putting here information, both what should be the compensation, what should be the next transaction, and we keep the application logic frozen, then we can run the automated procedure, at least from the author's perspective. Yeah. So we can simplify this further if we. Okay, dude. Everything is simple. I would like to have such a simple word. But yeah, we can simplify this further if we simply view a saga as a file containing a sequence of calls, individual transaction programs. Here, there is no need to explicitly begin or end saga, nor begin or end transaction commands. The saga begins with the first call in the file and ends with the last one. Furthermore, each call is a transaction. The state of a running saga is simply the number of transactions that is executing. This means that the system can take the save points after each transaction with very little cost. Such pure forward recovery methods would be useful for simple LLTs, so long-lived transaction. It's over 1 hour and a half, so we might forget. That always succeed. The long-lived transaction that computes the interest payments for bank accounts may be an example of such long-lived transaction. The interest computation of an individual account may fail through an abort transaction command, but the rest of the computation would proceed unaffected. Using operation system terminology, the transaction file model described above could be called exec or a script or a batch. However, all exec facilities we know of are not persistent in our sense. For instance, a failed exec might simply be restarted at the beginning without compensation. So I think that I have something similar to show, and I would be curious your thoughts. I hope that you are not sleeping yet, because this is the example of Saga that I put in my blog article about Saga, not about the database Saga, but business process. And it's kinda, I mean, I really didn't read this article today to prepare. I wanted to be surprised, but actually that looks like this commands, like this execution script, because this can be placed in a single file. So we have an event like cart finalized, and then we are telling that when we finalized shopping cart, then we need to initiate order. And when order was initiated, then we can send command request payment. And when we handle that payment was made, then we can record order payment. And once the payment was recorded, and then recorded that, then we can send package. If it was sent, then we can complete order, but we can also define compensation. So if product was out of stock, then cancel order. And if order was canceled, then discard payment. So this is our compensation. Probably we should put those compensation right after the previous steps in that document terminology, but kind of that's aligned. The only thing that we don't have here is the actual code of how to request payment, how to record order payment, but we can assume that each, at least in my description, that each send command is like a microtransaction. So microtransaction that it's shutting down the partial state of our processing. And so it's also like a save point. So once our system crashed, our services crashed, if we restart it, then we had some background process that can take it from there. So if we see that we wanted to send command, but we actually didn't send it, then hello, we can try to resend it. And from the microservice world, this can be like an outbox process. I'm curious if you agree. But let's move on and get back to our databases. So other errors. Up to this point, we have assumed that the user provided code in compensating transactions does not have bugs. Okay, that's good observation. But what happens if a compensating operation cannot be successfully completed due to errors? For instance, it tries to read a file that does not exist, or there is a bug in the code. So for example, we are parsing wrongly the file name. The transaction could be aborted, but if it were run again, it would probably encounter the same error. In this case, the system is stuck. It cannot abort transaction, nor can it complete it. A similar situation occurs if in pure forward scenario, a transaction has an error. So getting back to our blockchain analogy, this is why I don't trust blockchain, etc., because it's vulnerable to really human errors. Like if we put the code and freeze it, then it will be always failing. So yeah, but sorry for that. One possible solution is to make use of software fault-tolerant techniques along the lines of recovery blocks. Sounds smart. A recovery block is an alternate or secondary block of code that is provided in case a failure is detected in the primary block. If a failure is detected, the system is reset to its primary state and secondary block is executed. The secondary block is designed to achieve the same end as the primary using a different algorithm or technique, hopefully avoiding the primary's failure. The recovery block idea translates very easily into the framework or Sagas. Transactions are natural program blocks, and rollback capabilities for failed transactions is provided by the tech. The Saga application can control recovery block execution. After it aborts a transaction or it's notified that its transaction has been aborted, the application either abort the Saga, tries an alternate transactions, or retries the primary. Note that compensating transaction can be given alternates as well to make aborting Sagas more reliable. So I think Martin is close to what this is close to what we discussed. So it does their best to perform compensation, but if it cannot, then it just finishes Sagas and skips the unwelcome compensation. And I think that those alternate blocks are also useful for the scenario that I mentioned earlier. So let's say that we want to compensate payment, but we don't have money in our account, then we cannot do it. So if we predict that this scenario might happen, then we might have compensation for compensation. For example, I don't know, making payment or with some delayed or scheduling payment for a later. However, if we have a bug in the code, then I don't see how we can have alternate code block. Maybe besides the Pokemon exception handling, so catch them all and move on. Yeah. The other possible solution to this problem is manual intervention. The erroneous transaction is first aborted. Then it is given to an application programmer who, given a description of the error, can correct it. The Saga execution component or the application then reruns the transaction and continues processing the Saga. Fortunately, while the transaction is being manually repaired, okay, I was working in one system based on Oracle in the hospitality, and the old competitor that is still the main one, it's still run on Oracle. That was really the scenario. You were calling consultant. The consultant was going into like driving to your hotel It's called Opera by Oracle, and it was manually changing the stored procedures in Oracle. That was or customizing them. That was the official, and I'm afraid that it's still an official way to handle some issues. But in our case, it might be just a hotfix deployment. So in nowadays, or rolling back the wrong code if we notice that it's misbehaving. Hence, the fact that an already long saga will take even longer, yeah, obviously, will not significantly affect performance of other transactions. So that's fair. Even if we need to redeploy that with the hotfix, we other can proceed to some degree. At least, of course, it might create some ripple effect if we made the wrong state and we cannot compensate it because of the program error. Then we might have other errors made by other sagas or other application procedures, but that's another story. Relying on manual intervention is definitely not an elegant solution. Yeah, Captain Obvious, thank you. But it is a practical one. Okay. The remaining alternative is to run the saga as a long transaction. When this long-lived transaction encounters an error, it will be aborted in its entirety, potentially wasting much more effort. Furthermore, the bug will still have the corrected manually and the long-lived transaction resubmitted. But still, the advantage of having this transaction log, so knowing precisely what we did and what failed and what's not, is a big advantage, because then we can deploy new version of our application and fix it. So that's like, hello, event sourcing. That's how it works. But yeah, let's drop event sourcing for now. The only furthermore, the bug, blah, blah, blah. In the case of Saga, Saga will continue to be pending in the system until the repair transaction is installed. Fair. Implementing Sagas on top of existing DBMSs. In our decision of Saga management, we have assumed that Saga execution component is part of database management system and has direct access to the log. However, in some cases, it might be desirable to run Sagas on an existing DBMSs that does not directly support them. This is possible as long as the database can store large unstructured object in example code and save points. I really need to check if in 1997 they have write-ahead log, or was it the write-ahead log design impacted by this white paper? That's interesting. There are basically two things to do to run Sagas without modifying the DBMS internals at all. First, the Saga commands embedded in the application code become subroutine calls as opposed to system calls. The subroutines are loaded together with the application code. I'm not sure what's subroutine in this context, but let's go on. Each subroutine stores within the database all the information that Saga execution component would have stored in the log. For example, the begin Saga subroutine would enter an identification for the Saga in a database table of active Sagas. The save points subroutine would cause the application to save its state or a key portion of its state. In a similar database table, similarly, the end transaction subroutine enters into some other tables the identification of the end transaction and its compensating transaction before executing an end transaction system call to be processed by the tech. So yeah, it sounds like hacking, but I mean, that was the state of the art in the 1987, but still we can translate that easily to our application work nowadays. So one module or one service can store their state in their database. So in that sense, one module could be a coordinator of the whole process. There is a comment from Martin. I think that event sourcing references make sense. A rollback in Saga in the summary of correction transaction, which sounds very similar to adding compensating events to event streams. I got event sourcing vibes earlier. Yes, that's correct. Actually, I have even on my blog the article that relational databases are working like event sourcing. I will link that in the recording. But yeah, I think that this article is clearly also explaining why is it useful, not only from the technical, but also from the business standpoint, to have the clear log of what has happened, because then we can do such operation, and why forward like append only log is really beneficial to resiliency and so on and so forth. So yeah, I'm good that I wasn't pushing so much the event sourcing. I mean, event sourcing is also standing on the arms of the giants, right? It's not that it was invented out of the vacuum. The commands to store Saga information, except save point, in the database must always be performed within a transaction. Else, the information may be lost in a crash. Thus, the Saga subroutines might keep track of whether the Saga is currently executing a transaction or not. This can easily be achieved if the begin transaction subroutine sets a flag that is reset by the end transaction. 1. All database storage actions would be disallowed if the flag is not set. Note that subroutine approach only works if the application code never makes system call to its own. For instance, if a transaction is terminated by end transaction system call and not a subroutine call, then the compensating information will not be recorded and the transaction flag will not be reset. Okay, I think that this part didn't age well, but at least, or maybe just too late. But yeah, sounds like a bit of hacky. Second, a special process must exist to implement the rest of the Saga execution components function. This process, Saga daemon, would always be active. It would be restarted after a crash by the operating system. After a crash, it would scan the Saga tables to discover the status of the pending Sagas. The scan would be performed by submitting a database transaction. The transaction execution component will only execute this transaction after transaction recovery is complete. Hence, the SD will read consistent state. Once the SD knows that status of the pending Saga is, it issues the necessary compensating or normal transaction, just as the SEC would have after recovery. Care must be taken not to interfere with Sagas that started right after the crash, but before the SD submitted its database query. So I think that also can be translated that we might have some cron process or an outbox. So we are storing all the messages that we intend to send, and we have some background process that should be restarted once it failed, and that tries to process with the next, like sending next command, sending next event, to just keep the our process going. So that's fair. That's how it works. Also in the microservice works. After the transaction execution components abort transaction, for instance, because of deadlock or a user-initiated abort, it might simply kill the process that initiated the transaction. In a conventional system, this might be fine, but with Sagas, this leaves the Saga unfinished. If the tech cannot signal the SD with this occurs, then the SD will, so Saga daemon will have to periodically scan the Saga table searching for such a situation. If found, the corrective action is immediately taken. A running Saga can also directly request service from Saga daemon, for instance, to perform an abort Saga. The abort Saga subroutine sends the request to the Saga daemon and then, if necessary, executes an abort transaction. This is really important, and all of the operations, so all command handling that we are doing in the now, like in the Sagas as we know it, so to orchestrating distributed processes, needs to be wrapped in the Pokemon exception handling, and after that it needs to send an information, so an event that something has failed. So that's really important. So how much we have left? Still have left. And we are almost 2 hours. So let's speed up. As I said, this is an experiment, and it went a bit out of hands, but I hope that it's useful. So parallel sagas. Our model for sequential transaction execution within Saga can be extended to include parallel transaction. This could be useful in an application when the transactions of Saga are naturally executed concurrently. For example, when processing of a purchase order, it may be best to generate the shipping order and update accounts receivable at the same time. We will assume that Saga process, the parent, can create new processes, children, with which it will be run in parallel, with a request similar to a fork request in Unix. The system may also provide a joint capability to combine processes within a Saga. Backward crash recovery for parallel sagas is similar for sequential sagas. Within each process of the parallel saga, transactions are compensated or undone in reverse order, just as with sequential saga. In addition, all compensation in a child process must occur before any compensations for transactions in the parent that were executed before the child was created, forked. Note that only transaction execution order within a process and fork and join information constrain the order of compensation. If T1 and T2 have executed in parallel, so those two processes, and T2 has read data written by T1, compensating for T1 does not force to compensate for T2. At this point, remember the excessive use of the word simple in this article. Yeah. As I said, simple is not easy. Unlike backward crash recovery, backward recovery from a saga failure is more complicated with parallel sagas, because the saga may consist of several processes, all of which must be terminated. For this, it is convenient to root all processes fork and join operation through the saga execution component, so it can keep track of the process structure of the saga. When one of the saga processes requests an abort saga, the saga execution component kills all processes involved in the saga. It then aborts all pending transactions and compensates all committed ones. Forward recovery is even more complicated due to possibility of inconsistent save points. To illustrate, consider the saga of figure 8.1, so this one. Each box represents a process. Within each box is the sequence of transactions and save points executed by the process. The lower process was forked after T1 committed. Suppose that T3, so this one, and T5 are currently executing transactions, and that save points were executed before T1 and T5. At these points, the system fails. The top process will have to be restarted before T1, Therefore, the save point made by second process is not useful. It depends on the execution of T1, which is being compensated for. The problem is known as cascading rollbacks. So we run T1, and after T1 we run T4, but we didn't store the save point. So when we restart, then we will execute T1, and in theory we already executed T4, but we need to try to execute it again. And if we try to execute it again, then it might be some idempotency issue. So we might be calling the same stuff twice. So it would be good to detect somehow that it was already run. Let's see if there is something about it. This problem is known as cascading rollbacks. It has been analyzed in a scenario where processes communicate via messages or shared data objects. There it is possible to analyze save point dependencies to arrive at the consistent set of save points, if it exists. So kind of like some sort of Git branching. The consistent set can then be used to restart the process. With parallel sagas, the situation is never simple, since save point dependencies arise only through forks and joins, and transaction and save points order within the processes. To arrive at a consistent set of save point, the sec must again be in form of process forking and joining. The information must be stored on the log and analyzed at recovery time. The sec chooses the latest save point within each process of the saga, such that no earlier transaction has been compensated for. A transaction is earlier than a save point if it would have to be compensated for after a transaction that had executed in place of that save point. If there is no such save point in a process, that entire process might be rolled back. For those processes with save points, the necessary backward recoveries can be conducted and the process is restarted. So my understanding on the potential solution is that we should keep all the information of the past steps in each branch. So like in Git, then we know if we're restarting and this, and also the message that we forked. So we went two ways from here. And then we need to store whether what happened if we already used that. And again, having immutable log is kind of helpful here because we can see that, okay, we are at this save point and we went this road, T0, T1, T4. So if we again try to execute T4 after T1, if that has the same ID, so like an idempotency key, then we know that we might just skip it and move here. To arrive at a consistent save point, the sec must again be informed of process forking and joining. Yeah, okay. So designing sagas. The saga processing mechanism we have described will only be used if application programmers write their long-lived transactions as sagas. So, see, be like me, write your sagas explicitly. Joking, of course. Thus, the following questions immediately arise. How can a programmer know if a given long-lived transaction can safely be broken up into sequence of transactions? How does the programmer select the breakpoints? How difficult is it to write compensating transaction? In this section, we will address some of these issues. To identify potential subtransaction within a long-lived transaction, one must search for natural divisions of the work being performed. In many cases, the long-lived transaction models a series of real-world actions, and each of the actions is candidate of a saga transaction. So that's fine. So like a business commands, like perform some specific operation. So this is a potential transaction and part of Saga. So like pay order, start shipment, and so on and so forth. For example, when a university student graduates, several actions must be performed before his or her diploma can be issued. The library, inclusive terminology in 1987. That I like that. I like that. So yeah, but still, can be performed before his or her diploma can be issued. The library must check that no books are out. The controller must check that all housing bills and tuition bills are checked. The student's new address must be recorded, and so on. Clearly, each of the real-world actions can be modeled by a transaction. Fair. In other cases, it is the database itself that is naturally partitioned into relatively independent components, and the actions of each component can be grounded into Saga transaction. For example, consider the source code for a large operating system. Usually the operating system and its program can be divided into components, like the scheduler, memory manager, the interrupt handlers, etc. A long-lived transaction to add a tracing facility to operating system can be broken up so that each transaction adds the tracing code to one of the component. Similarly, if the data on employees can be split by plant location, then a long-lived transaction give a cost of living raise to all employees can be broken by plant location. Designing compensating transaction for long-lived transaction is a difficult problem in general. Really? I thought that everything is simple. For instance, if a transaction fires a missile, it may not be possible to undo this action. Fair. Luckily, we are not doing a lot of systems like that. However, for many practical applications, it might be as simple or difficult as writing the transactions themselves. In fact, Gray notes that transactions often have corresponding compensating transaction within the application transaction set. And that's a fair point because in business world, there are really compensating operations always. Just ask the business, how do you do it on paper? How do you do it? And if they say that no, that cannot be done, then ask enough whys, and they will tell you something like, okay, then if that happens, then I'm calling that this and that, or I'm sending this email to that person. And those are processes, those are compensating operations that we should model in our systems. This is especially true when the transaction model a real world action, told you, that can be undone, like reserving a rental car or issuing a shipping order. In such cases, writing either a compensating or a normal transaction is very similar. The programmer must write code that performs the action and preserves the database consistency constraints. So again, talk to business. It might be even possible to compensate for actions that are harder to undo, like sending a letter or printing a check. For example, to compensate for the letter, send a second letter explaining the problem. To compensate for check, send a stop payment message to the bank. Of course, it would be desirable to not have to compensate for such actions. However, the price of running long-lived transactions as regular transactions may be so high that one is forced to write sagas and their compensating transactions. Fair. Also recall that pure forward recovery does not require compensating transactions. See section 5. So if compensating transactions are hard to write, then one has the choice of tailoring the application so that long-lived transactions do not have user-initiated aborts. Without these aborts, pure forward recovery is feasible and compensation is never needed. And that's, from my experience, what we should try and aim for. So give user possibility to manually restart the business process. And that's what we had in our distributed process webinar, where we had the group checkout process. And if it was just supportive, so for example, we tried to check out a group of hotel guests, and we weren't able to check out 2 out of 5, then it's not a big deal. We don't need to have an automated compensating operation. We can check out those 3 guests, sort out the issues that had those 2 others. So for example, they didn't pay for their stay, and then restart the group checkout again with just those 2 people. So that's the best design, because compensation can be really difficult. And I agree with authors of this article. As has become clear from our discussion, the structure of database plays an important role in the design of Sagas. Thus, it's best not to study each long-lived transaction in isolation, but to design the entire database with long-lived transaction and Sagas in mind. That is, the database can lay it out in a set of loosely coupled components with a few and a simple inter-component consistency constraint. Then it is likely that the long-lived transaction will naturally break up into sub-transactions that can be interleaved. I'm not sure if that's a database design. Maybe it is, like with the transaction isolation level and write-ahead log, obviously. But I would still treat it more like application concept based on this article, of course, and my bias. Another technique that could be useful for converting long-lived transaction into Sagas involves storing the temporary data of the long-lived transaction in the database itself. To illustrate, consider a long-lived transaction L with the 3 sub-transactions T1, T2, and T3. If T1 long-lived transaction performs some actions and then withdraws a certain amount of money from accounts stored in the database, this amount is stored in a temporary local variable until T3 the funds are placed in some other accounts. After T1 completes, the database is left in an inconsistent state because some money is missing. It cannot be found in database. Therefore, Saga cannot be run as Saga, the L, so our Saga. If it were a transaction that needed to see all the money, say an audit transaction could run some time between T1 and T3 and would not find all the funds. If our Saga is run as a regular transaction, then the audit is delayed until our Saga completes. This guarantees consistency but hurts performance, and we are ending with the initial issue. However, if instead of storing the missing money in the local storage, our transaction stores it in the database, then the database would be consistent and other transactions could be interleaved. To achieve this, we must incorporate into the database schema the temporary storage. For instance, we add relation for funds in transit or for pending insurance claim. And this is important because it's one of the issues that I have in most of the Saga implementation I saw is that they are trying to claim that Saga has its own state. And I'm claiming that this is not Saga, but Process Manager. And of course, it's a potato discussion, but it's an important split because if we keep this temporary storage as part of the process, then it's much simpler to implement. Because, for example, we might not need this as a temporary storage. Maybe we could make it just yet another step of the Saga. And then we don't need to have another component for keeping the local storage of our Saga and potentially another point of failure, but we can just proceed with the original idea of the transaction and clear responsibility split between the Saga execution component and transaction execution component. Then transaction execution component is something that we get from database, and Saga is a clear application layer concept. Of course, that's my way. But I think that what he writes here is not contrary to that. But on the other hand, it's also stating that this is like an optimization, that Saga might have some sort of state, but it's better if it's still focused on the business process. So like funds in transit, pending insurance claim, so on and so forth. Also, transactions that need to see all the money must be aware of this new storage. Hence, it is best if this storage is defined when the database is first designed and not added as an afterthought. Even if long-lived Saga, so our Saga, had no T2 transaction, writing the missing funds in the database may be convenient. Notice that in this case, our Saga would release the logs on the temporary storage after T1, only to immediately request them again in T3. This may add some overhead to our Saga, but in return for these transactions that are waiting to see the funds will be able to proceed sooner, after T1. This is analogous to having a person with a huge photocopying job periodically step aside and let shorter jobs through. For this, the coveted resources, in example, the copying machine or the funds, must be temporarily released. So yeah, again, this is that's why I don't like when Sagas or process manager have their own state, because then they are like the single point of failure, and they need to be run sequentially. So it's, in my opinion, much better if we keep the transaction explicit. So in terms application, command handling explicit, and then we know precisely what's the responsibility. But coming back to the simple word, I'm a simple man and I like the simple solution. So maybe that's that. I respect if other people think differently, but I cannot put too much in my head, because then I cannot, I have a brain fuck. Yeah, this is my stream, so I can swear, but sorry for that. We believe that what we have stated in terms of money and long-lived transaction holds in general. The database and the long-lived transaction should be designed so that data passed from sub-transactions to the next via local storage is minimized. This technique, together with a well-structured database, can make it possible to write long-lived transactions or sagas. Conclusion. We have presented the notion of saga, a long-linked transaction that can be broken up into transactions but still executed as a unit. Both the concept and its implementation are relatively simple, and in its simplicity lies the usefulness. We believe that a saga processing mechanism can be implemented with the relatively little effort, either as part of DBMS or as an added-on facility. The mechanism can be used by the large number of long-lived transactions that are sagas to improve performance significantly. So I would say that from the technical standpoint, with the write-ahead log, transaction isolation, and replication, we have already some of that baked in our databases. From the business standpoint, I think that unfortunately, this is not yet the place that we are. So implementing sagas and processing them, there are still tons of way of how to do it. We don't have, as an industry, a common way how to proceed with that. Let me give my short summary of how I see that. So if we have a look on our database of our services world, so how we are treating Sagas nowadays, then I think that those microtransactions still stands. So if we are sending commands and each service has its own state and it can store the state and so do the save point and have the mechanism like an outbox pattern, CDC, whatever, to both shut down the state, so make a save point, and also schedule the message, so command that we want to trigger another operation or an event that informing that our operation has finished, then it's kind of like a Saga design, because in this case, begin transaction is like a command in our event-driven terminology. End transaction is like a event, because we are informing that something has happened. And once we got the event, then as I show you in the code, we got event, and event should contain all the information of what happens next. So if we have a central place like this Saga, and we have our event, and it contains all information to make the routing, so trigger another transaction or a compensation, then it's indeed simple, although not easy. So I think that I might be over interpreting that by my bias, but I think that it's quite close to what authors had in their mind. And it's really useful what they provided us, because I think that it really significantly affected our perspective on that. So if we have this like event-driven services that are issuing commands, storing the save point, so our state, and publishing a next step, so either event or command, then we can have easier handling of our Sagas. So I'm calling Sagas quite often like a lasagna, so or a sandwich. So it's like we are sending command, handling it, and publishing success or failure event. So again, it's quite close to what we had. So here, so we have the transaction 1, transaction 2. We can store a save point after each ending transaction and publish event that we finish this transaction. And then Saga can take it from there and taking our script, so our code, application code, trigger further steps. So this is how it can look like. So we are confirming shopping cart in our shopping cart module. Then our Saga is taking the event, initiating order, and then initiating order is like a coordinator of our Saga, so our Saga execution component. And we are requesting payment, then payment was made. We are telling to ship the product, and we are getting the information that product was shipped. And by that, we are getting those microtransactions, because in each operation, we can have the save point and we can push it forward. And in the case, we can compensate it. And in my terminology, Saga is like a DAM coordinator, which is, I think, the initial definition of Saga in this document. If I have to map it, we still have this central coordination, but we don't have this complicated temporary storage that was presented in the end. And process manager is this with temporary storage, because it's like a Saga, but with its own state. And choreography, it's like no state, no central coordination. We are just triggering a next message forward. So it's like this choreography is like this automated processing. So yes, Martin is asking whether Saga is orchestration. Yes, because we are orchestrating. We have this we have this script, as it was said. So we have the script that is like a central point. But we might also have like a sagas of sagas. So this command might start some another saga. And from this big saga perspective, we might not know it even, and we might not care. If so, this is this case. So this one saga is starting another saga, and we want to have this completion in the end of the general one, but this own can have its own timeline and so on and so forth. So I think that's kind of all. I think that yeah, it took us 2 hours and 20 minutes, much longer than I expected, but I hope that it's useful. Thanks, Martin, for staying longer. Indeed, I think that this is like a bit of event sourcing vibe, because it clearly says and shows why is it important to have append only log. Why is it important to store both events and commands? Because here we not only need to store the events, but also what we intend to do. Because if we store also command and we didn't get the save point or next event, then we should restart processing. So this is really important. And if Renaud has a great article about workflow pattern, and I think that workflow pattern is quite close to that because it stores both commands and events. So it gives us the full traceability of our process. And it's really, I believe, close to what we have here. So in a nutshell, I think that that this article and this white paper aged really well. And it's clearly visible how the ideas that there are in this article shaped both the technical implementation, so write ahead log, and so on and so forth, and also the DDD community and other logical application concept. So I think that's useful. I will be grateful for a feedback, especially for those that are rewatching that and get to this point. If that's useful, then I will try to continue that in the next month. So thank you. And thank you, Martin, for staying with me till the end. And yeah, see you next time. Bye.